Hi students, continuing with the same example that we were discussing in our previous lecture in the same series of normal distribution. The tennis ball has a diameter 6.7 centimeters with a standard deviation value of 0.3, and let's take the case when we are drawing a random sample of 16 tennis balls from a production lot. Then definitely we have to represent the entire sample with some value because we observe a variety of diameters of tennis balls in that sample of size 16 balls randomly selected, and the best way to represent the entire sample is to move your variable or to change your variable from x to x bar. Now in the previous series, the formula that we have used for random variable x was z equals x minus mu divided by sigma. With the help of this formula, we have transformed each value of x to corresponding value of z and then refer the z table to estimate probability from there. But now, since our variable changes to x bar, therefore we need to take help from the same formula, but this time we will change the random variable x bar. If we refer this value of mean mu, then this belongs to the variable x and the standard deviation also belongs to x. So we need to synchronize the z formula that we are going to write down for random variable x bar accordingly, and it is mu of x bar, and that's sigma of x bar. Now we need approximated value for these two newly created random variables, and mu of x bar, first of all we have to use this description that x follows normal distribution with mu and variance sigma square. So mean value can also be referred as expected value of x. Over here, this expected value of x is in fact equal to mu, and then variance of x is equal to sigma square. Now, since our variable is x bar and we need to assume the same thing, that x bar also follow normal distribution with mean mu of x bar and variance sigma of x bar squared. Now we can write down this x bar expected as expected value of x bar, and we need to prove that this is equal to mu. This is what we have proved already in case of dealing with numeric values. When I have given you the population data of population size 5, over there repeatedly, regardless of the sampling procedure that we did follow, regardless of the sample size that we did take, we have always ended up with mean of the sample mean is equal to population mean. Now we are going to prove this algebraically. So what I need to do, or what I'm doing, expected value of x bar, we take the left hand side quantity and we can write down expected value in this x bar formula in this way. Now expected value is just the operator that will be referring the mean of the random variable that we are using. So we can take this expected value operator inside the bracket, and this expected value operator will be applied on the random variable x, and this n comes as it is outside the expected value operator application. Now expected value of x We have in fact written down this entire thing, and this is indicating that expected value of x is equal to mu, and wherever we find expected value of x, we can simply substitute n substitute mu in place of expected value of x. Now we can read this as mu is added n times because the summation application up to n terms is indicating that mu is added n times, and mu is added n times can be rewritten as n times mu, because if mu we add n times, it is simple to multiply n by mu. That will give you the same answer. Cancelling these two, we end up with expected value of x bar equals to mu. Similarly, if we take variance of x bar, so again this can be written as summation x divided by n. Here, before applying variance operator inside the bracket, we need to consider the property of variance, that variance of ax is equal to a squared variance of x. Why is this so? Because variance operator is quadratic in nature. We take the whole square of the difference between each value of x and its x bar, raising it to square can give us the variance, okay, or the numerator of the variance formula. So therefore, whenever variance operator is applied on the product of constant and a variable, so variance of ax will become a squared times variance of x, because variance is quadratic in nature. So applying the same rule inside this squared bracket where variance operator is going to be applied on this entire factor, change will occur in the numerator, and its effect is when we bring this n outside the variance operator application. So this will become n squared, and variance with summation application will be applied only to random variable x. Now we can rewrite it down as n times variance of x divided by n. Again, we need to look at this. If we look at this according to this same description for what we are have given for random variable x, random variable x has a variance, population variance sigma square. So in place of variance of x, we can simply substitute sigma square, and that is sigma square divided by n. Again, we can read this as sigma square is added n times because summation up to n terms is involved or applied on this particular constant quantity. Therefore, we can rewrite it down as n times sigma square divided by n square, and this squared value will be cancelled out, and ultimately, consequently, we end up with this. And since variance is equal to this, we can rewrite it down at sigma s of x bar is equal to sigma divided by root n. So this is the value of sigma of x bar we get, and this is the value of expected value of x bar or mu of x bar that we get. Now, substituting these two reductions from 1 and 2 into this formula A, we get a new formula for z, that is z equals x bar minus mu divided by sigma divided by root n. Either this form we can use, or we can use this alternative form. This can be used when instead of picking up one observation as a sample from the population to represent the entire population, we are picking up multiple observations of any given sample size n. So this new formula of z to get our random variable x bar transformed to z must be used.